First of all, thank you very much for inviting me to come and speak here in Santiago. I really enjoyed the talks yesterday, and I'm looking forward to today and tomorrow. So yesterday, we already heard some presentations about applying JuMP or using JuMP to model energy systems, so kind of the front end. And today I want to start a little bit with the back end, so the solvers that actually solve the JuMP models. I'm at the University of Oxford, and I'm looking into algorithms that can solve very large convex conic problems. And the goal of this talk is to introduce you to this Julia package that I wrote that is able to, well, it performs very well on large convex conic problems, talk a bit about the underlying algorithms, some of the features, and why we use Julia and JuMP. And this is joint work with my two supervisors, Paul and Mark. Yeah, why do we care about solving large convex conic programs? That's something I have to explain every time I go home and talk to my family members when I explain what I do in my PhD. And the answer is quite simple. They actually appear in quite a lot of applications. So if you think about finance, there are some problems where you want to bound the risk of a portfolio of stocks. And these problems come out to be large semi-definite programs. If you want to design controllers for optimal and robust controllers for multiple agents, you get large optimization problems with LMI constraints. And then what we talked about yesterday, optimal power flow problems, and a lot of problems in graph theory are non-convex, but they have some kind of relaxation that come out to be semi-definite programs. This is just an overview of the talk. I want to kind of split it into parts. So the first part will be about how does the solver work and some example on how you can use it with JuMP. And the second part is about taking very large constraints and decomposing them into smaller ones, which actually helps you to solve problems a lot faster. Okay, so this is the problem we're trying to solve, or we can solve with Cosmo. We have an objective function that is quadratic. So P is a positive semi-definite matrix, and Q is just a vector. And then we have two decision variables, X and S. And we have an equality constraint that relate these two variables. And then we also have a constraint on S. So we say S is in some convex cone. Or it can also be a Cartesian product of cones. And that is actually quite a flexible formulation. So let's say you want to solve a linear program. You then just set P equal to 0 and say, okay, for all the equalities, S will be in the 0 cone. And for inequalities, S will be in the non-negative orthant. Similarly, if you want to solve a semi-definite program, you can just say, okay, I want my matrix variable S to be positive definite, and then you get a semi-definite program. Yeah, and we solve this kind of problem with a method called alternating direction methods of multipliers, or ADMM. And that's a first order method. And it's just a slide to review what ADMM does in case you're not aware of that. So ADMM assumes that you split your objective function in two parts with two different sets of variables, X and Z. And then you have some equality constraint on X and Z. Then you formulate the augmented Lagrangian. So you move the equality constraint into the objective function. That gives you this dual variable Y. And you also add what is called a regularization term that helps you with non-strictly convex problems. And then ADMM always does the same three steps. So in the first step, you take this augmented Lagrangian and you minimize it with respect to X. And that gives you your X iterate. And the second step is you minimize it with respect to the second variable, Z. And the last step is to update the dual variable. So that's quite a simple algorithm. And we take this algorithm and apply it to the problem format that I just showed you. So remember, we need to split the objective function into two parts, F and G. And this is our problem format. So the way we put our problem into this ADMM format is we take the two constraints, so the equality constraints, ax plus s equal to b, and the conic constraint, s in the cone, and we just move them to the objective function using this indicator functions. And the indicator function just evaluates to infinity if the variable is not in the set, or to 0 if it's in the set. So that's kind of an equivalent form of the problem. And then we introduce two dummy variables, x tilde and s tilde, and we say, okay, they are equal to x and s. And that way we can split the problem in these two parts with function f in terms of x tilde and s tilde, and with function g in terms of x and s. So we have this nice ADMM format now with one function, the other function, and an equality constraint. Yes?
Is the difference here in SCS is that you have the quadratic term at this level of formulation? Is that
The problem format is the same. SCS has a quadratic function. They don't have a quadratic function, and they use the same primal dual formulation, so they solve the primal and dual problem at the same time. Yeah, but otherwise it's very similar. And now we just apply the 3 steps that I showed you before. And what you get is this quite simple algorithm. You have these 4 computation steps. The step in line 3 is just essentially the minimization with respect to x tilde and s tilde. And when you want to solve this is always a equality constraint quadratic program. And steps 4 and 5 are projection steps. Step 4 just projects onto R, and step 5 projects onto the convex cone. And then in the last step, you update the dual variable. So this is pure ADMM. And now I just want to briefly tell you how you can solve essentially the problem in the blue box and in the red box, since those are kind of the main challenging subproblems in this algorithm. So first, the equality constraint quadratic program. We can solve that analytically by just writing down the KKT conditions for that problem. And we get then just a system of linear equations that we can solve. So this is the system of linear equations here. And that has some nice properties. So one property is that it's only dependent on the problem data. So P and A are the matrices from the problem. And sigma and rho are just parameters of the ADMM algorithm. So this left-hand side never changes. And that means you can just factor it once. And then at each step, you just evaluate different right-hand sides. So that's quite fast to implement. And another property is that this matrix is always quasi-definite, because the upper part is always positive semi-definite, and the lower part is always negative definite. And that allows you to always get a nice LDLT factorization. Yeah. So this is the first step. You solve the QP. And the other difficult step is the projection. And so projection is essentially you give me a vector and some kind of constraint set, and I tell you a vector in the constraint set that is closest to that vector. And it is quite easy to do if you have an LP or QP, then that operation is really cheap to do. It's more difficult if you get if you want to project onto the positive semi-definite cone, since you always have to compute eigenvalues and eigenvectors. And that doesn't scale very well if your problem size increases. So the operation to find the eigenvalues and eigenvectors is of complexity n cubed. So if you think about it, if you increase your matrix size that you want to project on, that operation gets a lot more expensive. Yeah, this is just an example of a problem that has a really nice form for our solver and that is really easy to solve with JuMP. So assume that I give you a portfolio of stocks, and I give you a matrix that tells you how the stocks are correlated. And you want to do something with this matrix, but for some reason, it's not really a correlation matrix anymore. And by correlation matrix, I mean a matrix that has positive eigenvalues or non-negative eigenvalues and ones on the diagonal. But I don't know, your colleague maybe deleted some like cells in Excel, so it's not really correlation matrix anymore. but you want to find the closest matrix to that is actually a correlation matrix. So what you can then do is, if you think about the variable x, which is the matrix we're trying to find, in terms of, not as a matrix, but as a vector, so you stack the columns of the matrix into a vector, then you can rewrite the objective function as a quadratic function. And then you have a constraint on the diagonal, so they are all ones. And you say, I want this matrix to be positive semi-definite. So if you want to do that in JuMP, assume you get this matrix C that you want to find the closest correlation matrix for. Then you set Cosmo to be your optimizer. You say X, I want X to be a matrix of the same size, and it should be positive semi-definite. You formulate this quadratic cost function, and then you just add the constraints that your diagonal is equal to 1. All the entries are equal to 1. And then you can solve this with JuMP. And I believe most semi-definite programming solvers actually get an error message here because they don't implement quadratic cost function. So you have to move quadratic terms into an additional constraint. So this is quite a nice form to solve this problem. And I did that for like increasing size of matrix C and for different solvers. So on the x-axis, you can see how the matrix that you want to find the closest correlation matrix for increases, and on the y-axis, you have the solve time. And one thing you can see immediately is that Mosaic and Sudumi, which are interior point solvers, don't scale very well if you increase the problem size. And it's not surprising that first-order methods, they perform a lot better. And actually, you can see that for large problems, Cosmo has a small advantage against SES, even though SES is written in C and Cosmo is written in Julia. And that is likely because SES has to take the quadratic cost term and put it into an additional constraint, which leads to more projections. Okay. So this was the first part of the talk. The second part of the talk is about how you can take very large positive semi-definite constraints and decompose them. They have a certain kind of structure. Yeah, so the idea of causal decomposition is that instead of doing this operation, instead of taking this constraint here where your matrix S is positive semi-definite, as I told you, this is quite an expensive operation if S is very large. So ideally, you want to replace this one large matrix constraint into multiple very small ones. And sometimes you can do that if your problem has a certain structure. So this is, again, our problem format. And if you look at the equality constraint with AI and B, if AI and B have zeros in common places, then S will also have zeros in those places, right? So if all the AIs and Bs have zeros in these places, then S has the same structure. And what we can then do is we can look for these subblocks and decompose this constraint. And we do this by analyzing the structure in graph form. So you can derive a graph based on the sparsity pattern, where you just put an edge between vertices that have a non-zero element in the matrix. And then you try to find the complete subgraphs in this graph. So subgraphs or complete subgraphs are graphs where all the vertices are connected to each other. So one example would be 1, 2, 6, another 1, 2, 3, and 4, and then 4, 5, and 6. And that gives you essentially the subblocks of that matrix. And what you can then do is apply a theorem called Eigler's theorem that states that if you can represent the sparsity pattern of your positive semi-definite variable with a graph, and you know the cliques of that graph, so the complete subgraphs, then it's equivalent to say the whole matrix is positive definite, or you can also say all the subblocks are positive semi-definite, and I can map the subblocks back to the original position in the large matrix. So this is the original problem that we get. And if we then apply the theorem after analyzing the structure, you get a similar form, but now you have a number of smaller semi-definite constraints. And then you have this summation term that maps these blocks back to the position in the matrix. And you can also do this with JuMP and Cosmo. So it's just a simple example. So assume you want to solve this problem with a linear cost function, and you have this one LMI constraint, AX plus S is equal to B, and S should be positive semi-definite. And then you're quite lucky because A and B have the same structure with these zeros in the top right corner and the lower left corner. So this would be an example here with A and B that have zeros in these positions. And if you now put this problem into JuMP, and you say, okay, Cosmo is my optimizer, and I want to decompose the problem. So you set decompose to true. You define the linear objective and the constraint. So B minus A times X is in the cone. And then you hit optimize. And then Cosmo analyzes all the positive semi-definite constraints and looks for these blocks. And as you can see here, it tells you originally the problem had one positive semi-definite constraint. It realized that it can compose this constraint. And in the end, you end up with two smaller constraints. And you can also see, so the sets that you're projecting on is a one PSD cone, which is 3 by 3, and one that is 2 by 2. And those are exactly these blocks in the top left corner and the lower right corner. Yeah. And you can obviously also do this with very large problems. So I did a benchmark where my variable S has this kind of structure here. So you have non-zero blocks along the diagonal. And in this case, they are 10 by 10. And I just solved this problem for a number of increasing blocks. So I believe from 50 blocks to 140 blocks. So this would be something like a constraint about 500 times 500, and then on the other side about 1,400 by 1,400. And what you can see here is, again, the solve time of Cosmo without decomposition, with decomposition, and SCS. And you can see that Cosmo without decomposition and SCS behave similarly. SCS is a little bit quicker for some problems. But what you can actually, what's a bit more interesting is that if you turn the decomposition on, then the solver scales very well and can solve problems a lot quicker. Because instead of doing a 1,400 by 1,400 projection, you actually just do 140 10 by 10 projections, which is a lot quicker. Yeah, so we put all these ideas into the solver Cosmo. It's written in Julia. It's based on ADMM. We support LPs, QPs, SOCPs, SDPs. We're also able to detect infeasible problems. One thing that we currently work on is to use multiple dispatch to allow the user to define his own convex sets. So if you have a fancy convex set and you know how to project on it, we want to make you, or want to allow you to project on that or add this as your like custom constraint. And we support the latest versions of MOI and JuMP. Yeah, and some of the future work is trying to accelerate the convergence of the ADMM algorithm. And so if you have a large positive semi-definite constraint, and you can decompose it into, let's say, 140 small ones, ideally you want to project all of them in parallel because they're independent of each other. So you theoretically could project all of them in parallel, which would give you another speed up. Yes. The package is available via the Julia Package Manager, and all the documentation and code is available online. Yeah, thank you very much. Yeah. Miles.
Have you thought of a GPU version?
Yeah, so this is one of the next steps we're looking at, and look if we can do that in Julia as well. Yeah. Juki?
How tied to your code for loading? Because I was talking to Ben last week. Most of the servers, they don't have horizontal conditions, and that's something you definitely can do upstream. So one thing we could do is a package that does horizontal condition that passes to all servers.
Yeah.
The composite problem, because it only depends on the matrix.
Yeah.
That's it.
Yeah. I mean, this is actually kind of what Cosmo does. So we don't, when we do the core decomposition, we don't touch the core solver. It's basically happening before. Yeah. So. Yeah.
Were you able to get dual variables? Because like ATM just equals
Yeah, we also get the dual variables. Yeah.
afterwards.
Yeah. Yeah.
How is it usually, or is it based on components, other like
It's pure Julia. Yeah.
Yeah. So do you return certificates of infeasibility?
Yeah. So there's this is essentially some of the theory that was developed by one of my colleagues who was involved in the OSQP solver, and they found a way to looking at the iterates of your variables and then using those as a certificate for infeasibility.
Thanks, Michael.